So now seems like a good time to get started. I want to welcome everyone who is turning up on the attendee list here. It seems like we have a good number of people interested, and for good reason. Today is the fourth and final webinar in our spring MCS RCN webinar series. And for more information on what's happened already in that series, you can go to our website, sc4dmcs.org/webinars. Check out, we post the webinars on that page and on YouTube when we're done with them. Today's webinar is on a topic that's kind of central to what we're trying to do here with the Modeling Collaboratory as part of SC4D. And I won't say too much about that. I just want to introduce two members of our steering committee who will serve as the moderators for today. It's Mark Behn and Alison Duvall. So I'll turn it over to Mark, I believe, and we'll get started.
Actually, I think we're turning it to Alison first.
That's fine. Hi, everyone. I'm Alison Duvall from the University of Washington, and it's my pleasure to introduce our two panelists today for this webinar. And they are Phaedra Upton, who is a senior scientist and team leader of the geodynamics team at GNS Science in New Zealand, and Greg Tucker, who is a professor of geological sciences and the director of the CSDMS at the University of Colorado in Boulder. And I'm going to turn it over to Mark to say a little bit more about what they're going to talk about today.
Yes, so one of the goals of these this webinar series is both to highlight some really cool science that's going on from some top people in the field, but it's also to talk a little bit about how people start working together and how collaborations are born, because a lot of the goals of the Modeling Collaboratory, as you can imagine, have to do with collaboration and bringing people together, and that's really what we're trying to facilitate through the Modeling Collaboratory. And so today, Phaedra and Greg are going to talk to us about their research, but also about what brought them together in their collaboration. And so Phaedra is going to start. She's going to talk a little bit directly to that question, and then also talk about some of her work thinking about the role of erodibility and how that can be added to coupled models of landscape dynamics. And then she's going to hand that off to Greg, who will then talk a little bit about the CSDMS modeling community and some of the tools that CSDMS has been developing and facilitating for public access. And this is a really amazing clearinghouse of different software codes that CSDMS has made publicly available and has been building and developing over the last decade. And so the way this will go is I'll turn it over to them. If you have questions at any point throughout the presentation, just type them into the chat window, and I'll interject them as we go through the presentation. So without further ado, I'll turn it over to Phaedra.
Okay. Morena, and good morning from New Zealand. Thanks heaps for the invitation to talk here and for tuning in and listening. So I'm just going to share my screen, hopefully. Ooh. Share screen, share. Okay. Right, so yeah, so I want to talk a bit first about how Greg and I ended up working together. So I spent some time in the United States, actually, at the University of Maine, where I was postdoc and then researcher and doing some teaching with Peter Coons. And I was very much into geodynamics then rather than the tectonic geomorphology. But I met Carl Mueller, who's at Colorado, structural geologist, and that was because he was working in Taiwan, and he was struck by the spatial coincidence of this region of low topography within the Taiwanese mountains and the area that was uplifted by the 1999 Chi-Chi earthquake. And so he wanted to see if there was some relationship between the two. And the previous ideas of the origin of that embayment were that it was related to something offshore, or that it represented a change in the strength or dip of the décollement. But he wondered, because this was a region that appeared to be uplifting rapidly. It was a topographic low. It was also full of sediments, whether there was a surface process connection, whether it was an erosional feature or whether it reflected something about the variation in material properties, because there's a really strong gravity low there as well. So I started talking to Carl, and we ended up thinking about doing some simple geodynamic models, and we put in an NSF proposal, which Greg was part of, and so that was how we came together. And then CSDMS has also proved to be a really important part of us continuing to work together. So for this project, I ran these really simple 3D geodynamic models using FLAC 3D, which is a commercial code that I've been using ever since my PhD. And I put on some very, very simplistic surface boundary conditions. Basically, I just tried to remove material at an imposed rate. And the results we suggested that the erosion and the variation in material properties were important, that the erosion of this basin did mean that there was more uplift being focused into this region. But it was a very simple model, and particularly it was just one-way coupling. That is, the erosion influenced the geodynamics, but the erosion was totally imposed. There was no feedback to whether that was influenced by what was happening in the geodynamics. And we also our only surface process we were looking at was erosion. We couldn't, in this system, we couldn't put any sedimentation into the basin, despite the fact that we knew from the geology that it was full of sediments. And this is one thing that's really important. Carl was great. It's really important for us modelers to get out in the field and see the rocks and see what's there. So I was lucky enough to go to Taiwan a couple of times with Carl and the students, and I really would not have had the understanding of this region that I ended up with had I not been in the field, watched what they did in the field, what was important to them, and also gave me the chance to be there and ask questions. But so between talking to Carl and talking to Greg, could we couple child to FLAC, and could we start to actually look at these processes in more detail? And so that's what Greg and I tried to do via trips for me going to from Maine to Colorado. And basically the idea was that we would build the same model in our two models, the same geometry. I would run the geodynamics, so I was calculating velocities and stresses and how the surface of the model was changing, and then I could export that position data, give it to Greg. He would have that position data in child, run child, put the surface processes on, calculate whether erosion, deposition, what was happening, get new elevation data, export that, feed it to me, and I would impose that as my surface process onto the grid of my model, and we'd loop it. It was complicated, and it took us a while, and particularly my model has a rectangular grid, child has a irregular grid, so there was getting the interpolation between the two it took a while. But we kind of got it running. And we don't really have any results for Taiwan because we did kind of lose momentum. I went back to New Zealand, I got a new job. Anyway, but momentum arrived in the form of our PhD student, Sam Roy. So in the meantime, Peter and me had written a geomorphology paper where we were really looking at, from a geodynamics point of view, how material strength and material properties that we could calculate in geodynamic models or by thinking in a geodynamic way might influence surface processes. And sort of parallel with that paper, we wrote an NSF proposal, which Greg was a PI on as well, which got funded, and it funded Sam's PhD. And so his PhD was exploring the links between tectonics and landscape evolution. And so he did a number of things, which I've listed here. He did use field observations to ground truth. He came out to New Zealand and used several different fault zones and areas to really look at cohesion values, the strength values, and erodibility. He took where we'd got, well, first he took child and modified child so that he could put in a variable erodibility in 3 dimensions. So he could take geological structures and put them in 3 dimensions into child. He also took our initial flat child coupling and made it work and run, and he added this cohesion erodibility link. And then he used these models, and he did a series of models, which I'll go through, where he sort of isolated different effects. So it looked initially at surface displacement, river erosion, the effects of rock damage and river erosion, and then combined it all into one dynamic model. And yeah, a series of papers that I've just put here that were the result of his PhD, which really outlined a lot of this work. So initially, so what's the isolative effect of surface displacement on a model? Fingers crossed, these were misbehaving this morning. So this is just really 3 simple models. One that is a model of a convergent margin, transverse margin, and then an oblique margin. And if we just run, oh, they're working. So this block is uplifting, this one's moving to the side, and this is oblique. It's a combination of the 3 of them. And so we see that in this system, is as we'd expect, you know, the rivers cut back, we get a dendritic pattern because it's a homogeneous material. Where we have a transverse, so this is moving relative to this. We see that reflected in the river systems. The rivers do reflect what's happening. Here they reflect the fact that the 2 blocks are moving relative to each other. And where we have an oblique boundary condition, we kind of get a combination of the 2. So here's the main river trunk, and it's flowing along because its outlet has been moved relative to its source. And this is kind of what we see in the South Island of the Alpine Fault of the Southern Alps, where we have quite oblique boundary conditions. And so this block is moving relative to this block. Then he took the damage erodibility link. So these are just, did a lot of field work in New Zealand looking at, so this is the Alpine Fault, the bedrock, the protolith of the Alpine Fault and cataclasites. So he took field estimates of cohesion. So scalar and Dietrichs had shown that the erosion rate is inversely proportional to the rock strength. So that is that the erodibility is a function of 1 over square root of cohesion. So if we can go into the field and estimate cohesion, then we can estimate the erodibility, and that's what Sam did. And then he built models where he put a damage zone in, so representing a fault zone, which is weakest in the center and then gets progressively stronger out into the intact bedrock. And so similarly, it's most erodible in the center and gets less erodible as you go out towards the bedrock. And so in the next example I'll show you is models run with vertical fault zones using child and looking at what's the effect of just rock damage in a model. So there's 3 models again, no weakening, so this is just a homogeneous material. Here we have a zone that's 30 times weaker, and here we have a zone that's 3,000 times weaker. And because it's a 1 over square root relationship, this means that the rock in the damage zone here will erode about 80 times more rapidly than the bedrock to the side. And so what we see, of course, is that this is where there's no weakening, we get that same dendritic pattern. Here we definitely see that fault zone, that weak zone, more erodible is dominating the topography, and when it's super weak, it really dominates the topography. And if I try and run them again, we see just how quickly this one goes. It's so much faster. And so then once this has eroded, it's controlled by the base level, and the sides erode at the similar rate to this. And so here's the Grand Canyon and the structure. We just see the Bright Angel fault here as an example of where we can see the structure, we can see the fault zone in the topography because it's a weak zone and it's eroding more rapidly. So it turns out that the rate of incision is a function of the dip of the structure that's being eroded. So where you've got vertical structure, weak zone, that erodes really rapidly, and then whereas when it's dipping, so when it's dipping, this is the weak zone, it'll erode rapidly, but then as it keeps eroding down, it starts hitting stronger rock again. So it actually has to remove this strong material before it can get down to the weak material again. And so I'll just run this wee movie, which just shows you the relative rates of these two structures being created. And so here, as you increase the dip of the fault zone, you increase the rate of incision into that structure. So it's most rapid when it's vertical, and it's not controlled by the strength of this material out here. It's just controlled by the strength here and the base level. Whereas when it's dipping, it's controlled by this weak zone, but also having to erode the stronger zone. How am I doing for time? Okay, so then he put it all together into, took his modifications to child, so that we've got child, it has a variable erodibility in a 3D structure and coupled with flak. So he's combining the effects of the displacement. In the geodynamic model, we have a strain softening, so we calculate where the strain is occurring, and where strain occurs, we get strain softening, so we get a reduction in cohesion and friction angle. And that is able to then be, that pattern of cohesion is taken from flak, from the geodynamic model, into the surface process model, into child in this case, and it goes back and forward. His model also included the precipitation. So this is the outline of the South Island. This is the Southern Alps, and we have a very strong orographic effect. So we use that as a basis for the climate that we're imposing on this model. So as the mountains build up, the orographic effect increases. And in this way, we could start to look at this. We can start to see how the erosion influences the stress state. So we're getting that feedback from the surface processes to the geodynamics, which we didn't have originally. So again, we have two models to really look at how the processes. In this top one, there's the geodynamics and the erosion, but there's not that feedback. So we're not, even though we're calculating strain and we're getting high strain zones in this model, we're not feeding back a reduction in erodibility, whereas in this model we are. So we see the mountains being built up, we're getting an orographic precipitation over here. We see the river system flowing down valley, as you'd expect, down the slope. And it's a dendritic, and it cuts through. Whereas in this case, we're ending up with these fault zones cutting this way. And because when we form fault zones, we get strain softening, and here we include that erodibility factor, we see that we get rivers forming down these valleys. The boundary conditions are such that this is the outlet, so it still has to cut through. We still cut through this stronger bedrock, but we cut through here really quickly. I'm not sure if I can just run those again. So we see about now is when it really starts to focus in onto these weak zones, because the amount of weakening is enough that the reduction in erodibility is high enough that it erodes more readily. So this is the river map that we end up with. So downslope versus really controlled by the structure. It's really controlled by the faults that come out of the model. And we see that feedback too. so this is crustal shortening, so it's, or strain. So these are the high strain zones in red. And we see that where we have erosion taking place in these high strain zones, we're actually focusing strain into that, more strain into these regions. So there's a positive feedback, more erosion, more strain, which would lead to more softening, weakening, and again, more erosion. These models are orthogonal. We never managed to get oblique models, but this is what we can sort of relate this to the Southern Alps. So here's the Alpine Fault down here. We've got these, so we've got high mountains here, these short, steep rivers on the western side of the Southern Alps, which are like the short, steep rivers we're seeing over here. And then these long rivers here, which pretty much are all in fault zones. So what we're seeing here is that the structure, the fault zones that we get, and the reason that these are not perpendicular to the boundary is because this has an oblique boundary. It's oblique rather than orthogonal. But we see that the rivers align to the structure. They align to where the faulting is occurring. And we talked about this in this paper in Geomorphology in 2012. So in this case, this is purely a geodynamic model where we put those boundary conditions on, and this is cohesion. So we calculated the cohesion structure that we would expect. And because this is oblique, and also because there's change in material properties, which I haven't got time to go into, we get these fault zones, regions of low cohesion, therefore regions of low erodibility, that are both parallel and perpendicular to the plate boundary, which is similar to what we get in the South Island. So I just want to put it all together. There's lots and lots of components that are really important, and we've managed to bring some of them together in this coupling that I've talked about. And it really, often what you end up putting into a model is partly what you think are the most important ones, or what's the particular process you want to investigate. So we've talked a lot about material properties, cohesion, how cohesion and erodibility, surface processes, and obviously the tectonic boundary conditions. I haven't really talked about the stress much, but they're all interconnected. And so to really understand a region like Taiwan or the Southern Alps, we really do need to look at the tectonic process, the surface process, but really consider the material properties that obviously impacted by the tectonic processes and the stresses that are imposed, and we've shown that they're also influenced by the surface processes, which in turn influence the stresses. So it's very coupled, but we're making good progress, and Greg's now going to tell us some tools that CSDMS has to help us with this. So I'll stop sharing.
Phaedra, before you go, there were a couple questions related to kind of tying these models back into different data sets. So one of them was a question about the total amount of displacement on these faults in New Zealand, and whether it's consistent with the amount of weakening that you might see.
So, I mean, some of the Alpine Fault in New Zealand has over 400 kilometres of displacement, and has a fault zone that the really weaker part of the fault zone, or the gouge is metres, and then the cataclysite is tens to 100 metres, and the whole fault zone is about 1 kilometre, and so it's a really big damage zone. Some of the Marlborough faults that Alison's worked on, those damage zones would be hundreds of meters. And those faults, because they're so easily erodable, are actually really difficult to go and put your hands on. So when Sam went into the field, we chose sort of a side fault, one of the little splays off the Marlborough faults, because it wasn't as deeply eroded, and when we went up into a saddle, we were able to find fault gouge that was, along the line of the valley. so I'm not sure that I fully answered the question here. There's also a lot of like drilling. There's there was drilling in Najima in Japan, some of the San Andreas fault, some of the work we did from the Alpine fault drilling. So where we've sampled faults through drilling, and then experiments have been done on, and so there's quite good experimental data of the cohesion, the frictional strength, and then how we can relate that to the erodibility.
And also, is there any influence of the fault strike relative to the trunk stream geometry on the erodibility? So essentially the orientation of the interaction between the two structures?
Yeah, actually, Alison could probably answer that. I mean, so some of the work that I've been doing with Alison and her students in the Marlborough faults, because there you've got an old, the tectonic stresses are changing as the plate boundary changes, and so you've got one set of faults that are quite well developed and but no longer active, and then they're being cut across by these new sets of faults. And so there, Alison really showed that in some places the new faults were well developed enough that they were dominating the topography, but in other places it was a mixture, or you're still being dominated by the older structures. And that, I think, yeah, is really a function of how advanced and how much damage has occurred on these old structures, on these new structures cutting across the old ones. But also often this strain weakening, sometimes it heals, but sometimes it doesn't. So you still see inactive structures in the landscape because it still is at damage zone. And once a river is in a valley, it takes quite a bit to cut it out. So you do need a strong structure cutting across.
Mm-hmm.
Alison, do you want to add to that?
No, that was exactly, you said everything I would have said.
Great. Well, I think in interest of time, we'll move next into Greg's portion of the discussion.
Okay, thanks, Mark. Let me just share my screen. All right. Hopefully everybody can see that slide okay. So I think Phaedra's given a great example of the kind of scientific discoveries you can make when you're thinking about coupling between different aspects of the tectonic and surface process system. I thought I'd say a few words about the software technology that makes that kind of discovery possible. To start, when we first started doing this back circa 2005, I guess it was, we had these two codes that we wanted to put together to try and develop some insight into the coupling. One was a landscape evolution model written in C++, with a particular idiosyncratic design, but open source. And the other, as Phaedra mentioned, was FLAC 3D. So it's this very powerful but commercial and proprietary code that that we couldn't get inside of. And so I just saw a message saying that people can't see the screen. Let me pause here for a second and just try this again. Share. That's better? Okay, awesome.
Yeah, I'm not sure why it's not working for everyone, but it looks good for the panelists and for at least some of the attendees. So maybe it's a mystery.
I'll tell you what, just to make sure this is going to work for everyone, I'm using two monitors, so that may be messing things up here. So if I just unplug from one of them, hopefully that won't bring us to our knees here. Okay. Hopefully this is working. Okay, so we have these two codes and we need to stitch them together, and we can only get inside one of them if we needed to.
You're not
And so
sharing
we
now.
have, sorry?
I think, yeah, no,
I don't think you're sharing now.
it's just your face.
Oh, really?
I think many of us could see it before, but not everyone, and now I don't think anyone can.
Well, now it still gives me the option to share. I don't know if that's relevant. Oh, yeah.
About now.
Yeah.
Now.
And
I
still
can see
now?
everything.
Yeah? Somebody give me a
Yes.
thumbs up. Okay.
Yes.
Thanks, Alison. Okay, so here's the challenge, that we need to couple these two things. And the way we did it was, okay, both these models create output files in their own particular idiosyncratic format. So we ended up writing a bunch of MATLAB scripts that would, and Sam greatly improved on this, they would take, they would run one model and then take its output files and read them in and translate it into the format of the other model, and then run that model for a small bit of time and then do the same translation back and forth. So it worked, as you could see from Sam's results, but it wasn't especially elegant or scalable solution, and not the most efficient solution. So trying to, and that costs time, right? That's time, that's extra time in developing this kind of thing that could be spent on more science. So I'm going to say a few words now, as Mark mentioned, about the Community Surface Dynamics Modeling System, because one of the things that organization has worked on is trying to find solutions that reduce that time to science and make it easier to do this kind of coupled modeling. So CSDMS, the acronym stands for the Community Surface Dynamics Modeling System. It's kind of a mouthful, but if you say it with a soft C and a hard D, it sounds like systems or systems. So you hear people call it systems. And it's an organization that was founded back in 2007 with an initial grant from NSF, and it focuses on Earth surface processes. So it's a community of communities who think about everything from engineering timescales, so think landslides, coastal storms, storm surge, turbidity currents, and that sort of thing, all related to sediment and topography or bathymetry. And people who think about geological timescales, so mountain building, deltaic deposition, coastline evolution over long periods of time, and that kind of thing. So systems is, it's currently a community of approaching 1,900 members. It's easy to become a member. You just sign up online or you attend a meeting. It spans about 70 countries and several hundred academic institutions. Despite all that, it's a small National Science Foundation currently supported program. And the funding supports a small group of people in what's called the integration facility at the University of Colorado Boulder. So that's where I'm calling in from. This is a little over a half a dozen of us at the moment, including 2 senior scientific software engineers, a couple of postdocs, and a program coordinator. And this small group of people works really works in 3 areas, and I'll touch on all 3. So the 3 key areas are community, computing, and education. And I'll say something about each of those, but I'm going to focus on computing tools and tricks that try to accelerate and make more efficient this process of model exploration and coupled modeling. But first, a little bit about community. So scientific software, you know, people have said that computing nowadays is in many ways the 3rd pillar of science after theory and experiment, or in the geosciences, observation. And in many ways that's true. The Nobel Prize in Chemistry some years ago was awarded for computational chemistry. And it's an indication that computing, not just in the geosciences, but across the spectrum of the sciences, is becoming an indispensable part of what we do. And that means software. And so, like it or not, many of us, even though our training may be in geoscience or biology or whatever, are de facto becoming part-time software engineers. So to do community software development, well, you need to have a community to begin with. You need to have people who feel they're part of a community. One of the things that systems does to try and build community is to hold a series of workshops and meetings. Some of you participated, for example, in the workshop on coupled tectonics and surface processes that was co-organized with our sister organization, CIG, the Computational Infrastructure for Geodynamics. This is a little bit of a bittersweet slide for me because this is the meeting that we were going to have this May, and it's not going to happen as an in-person event now because of the epidemic. There still will be some online virtual activities for those of you who aren't thoroughly sick of Zoom activities and events. But that's an example of community building. Another thing that we've done that's maybe more relevant for this conversation is something Mark mentioned, and that back in 2007, when Systems was first formed, there was an experiment that was done. At that time, my sense anyway was that a lot of the geosciences, when it came to modeling software, the model codes were treated a little bit as trade secrets. There were some exceptions to that, but that tended to be the default pattern. And each lab had its own model that it would share with, let's say, alumni of that lab, but not share with the rest of the world. So the experiment was this: if we build a web-based platform and invite people to share their codes, along with some metadata and other kinds of information, will they do it? And at the end, yes. And so today, this model code repository, which is Systems Model Repository, now lists and catalogs 200 some odd model codes and approaching 90 or so tools. And you can see some of them listed here in this screenshot. They run the gamut from small single subroutines to large integrated model codes. They span domains from ecosystems to geodynamics to coastal and terrestrial models. In fact, we have here the two co-chairs of the Systems Geodynamics group, Phaedra and Mark. So as an exercise in sharing, that was a success. And today the repository, even though there are GitHub and Bitbucket and other great platforms for code sharing, it still acts as a kind of a central clearinghouse with all kinds of information and kind of one-stop shopping. So that's one form of community building. The other thing, another ingredient you need to build a community around modeling software is education. You know, we're trained scientists, and yet we're being called on to work with software as a tool, and that requires some learning for many of us. So some of the things that Systems does in education include running a series of webinars. So this is an example of some recent and upcoming webinars on programming-oriented topics. There's also science-oriented topics, webinars about particular model codes and that kind of thing. We run an education repository, and in fact have been doing a lot of work on this lately to help benefit all of those who are instructors who have suddenly been forced to shift to online-only instruction. You can find labs and things like that. And what we hope will be a summer school running this summer. We'll see what happens. Maybe it'll be put off by a year. But so far, we're planning to run the first of what we hope will be an ongoing series of summer schools. So these are 10-day immersive experiences aimed at early career scientists. So graduate students, postdocs, early career faculty, and so on. So that's a little bit on education. And I'll say a few words then about software technology, computing. So to help get me in the mood, I went back and looked at one of the early documents that led to the founding of CSDMS. And it has this great sentence that says, CSDMS is envisioned as a modeling environment. So not a single numerical model, but a modeling environment containing a community-built, freely available suite of integrated, ever-improving software modules aimed at predicting the erosion, transport, and accumulation of sediment and solutes and landscapes and sedimentary basins over a broad range of time and space scales. I think if I had been a little older and wiser when I saw that sentence, I might have been very nervous because, of course, it's a tall order. This is what the community said they wanted. We don't want a single, say, global numerical model, which would have been challenging, but not as challenging. But we want something more flexible. We want something that's plug and play, where you can interchange parts. And when you have a small budget and a small team with a big task, the key is to try to leverage resources wherever possible and leverage community efforts. And that mandate then has given rise to the, I guess, collection of tools and protocols that we have now, which come in 4 complementary pieces. And I'll say a few words about each of these. It starts with an interface standard, and I'll explain in a minute what I mean by that. You need language interoperability because our community works in different programming languages. You ideally have tools to help people build the next generation of numerical models more efficiently than the old-fashioned way. And then you need some kind of a framework that can plug the pieces together and allow you to reasonably efficiently couple models as components. So let me give a couple of definitions. When I say model here, that's a word that, it's kind of an unfortunate word in science because it has so many different meanings. But here I'm talking about a self-contained computer program that simulates some aspect of a system. That's contrasted with the idea of a component, which is similar, but it is an interoperable software module that could act alone or as part of an integrated simulation system. So one of the goals is, because the community has written lots and lots of these things and is always writing more, in order to create an integrated system, you ideally want to be able to turn models into components. And that ends up being a process where the metaphor is wrapping, like wrapping a present, where you provide a relatively thin layer of additional software that allows what was a standalone piece of software to act as one component. So to make that possible, one of the things you need is this idea of a standard interface. Standard interface, it's something that in many ways we're accustomed to in our day-to-day lives in dealing with technology, right? So a USB cable is a standard interface that works across devices and manufacturers. If any of you have rented a car recently, you probably didn't worry too much about what kind of car you were going to get. And in fact, it probably wouldn't matter whether it's an itty bitty little thing or something gigantic, because either way, you would expect a standard interface of controls, right? I mean, imagine a world in which every single make and model of car was designed by a graduate student sitting in a lab, basically making it up, not to diss graduate students. I mean, I was one too, we all were, but if each of us is inventing our own interface, the automotive world would be a very different place, right? So standardization helps. And in the case of numerical models, this idea of a basic model interface is really at heart just a list of functions. It's just a standardized set of functions that do things like initialize a code to get it ready to run, update it. So think about it, if it's a time advancing model, it solves one time step. To query its values, tell me what's your cohesion at a particular location, or what is your velocity. You might want to set values. Now, this is where coupling becomes key, where I can tell a particular numerical model, no, you're going to change your cohesion value from 5 kilopascals to 3 kilopascals or whatever. And you might want to have a function to clean up at the end. So these are 5 of what ends up being about 30 odd functions, and a numerical code that implements these functions can be said to be compatible. It's a BMI standardized model. So that's one ingredient. Now, the next ingredient that you ideally need is something to handle language interoperability. The 2 pie diagrams on the left show the mixture of different languages that have been used by the Earth surface processes communities in the systems model repository. And it differs a little whether you count it by lines of code or by individual codes, but the message is that our community likes Fortran, likes C and C++. Some people like to work in MATLAB and Python, and there's not much in the way of other languages, Java and COBOL and whatnot, fortunately. So in order to achieve compatibility between these different languages, the integration facility has written a set of tools that will provide a kind of a front end such that that model can be operated in Python. So we've explicitly chosen Python as a coupling language because of its growing popularity, its flexibility, and so on. So that's language interoperability. Then a third thing that's helpful is to have a set of tools that make the process of creating a new model easier than it would otherwise be. If anybody has ever had the experience of trying to write a numerical code from scratch, it can be a pain in the neck, right? You have a lot of challenges, tasks that involve essentially reinventing the wheel. You know, for example, what if you wanted to read some parameters from a text file? Well, you have to write all that code. So to help address that need, we've developed a Python language toolkit called Landlab, which is really just a programming library that automates some of the kinds of things that are common in model building. That includes creating grids of one sort or another. And I should say it's explicitly for two-dimensional numerical models. Someday maybe it'll be 3D, I hope, but at the moment it's for 2D models. But it deals with grids, it deals with formatted input-output in common standardized formats, and it allows you to package particular bits of functionality as reusable components. So think if you have a numerical solution to a 2D diffusion equation, you can package that as a component. Somebody could pick that up and use it as part of their own future integrated model. So this slide shows some examples with tectonic anticlines to post-glacial works and distributed shear, stratigraphy, landsliding, overland flow, eco-hydrology, and a bunch of other things. So that's Landlab. And the final piece that I want to tell you about is a framework for coupling together model components. We've been through several different iterations of this, and initially starting with graphical user interface based coupling frameworks. And one of the things we learned from that is that the scientific, or at least the geoscience community, really likes to be able to get their hands dirty and write scripts, which is something you can't do with a graphical interface. So we've ended up taking what was originally the back end of such an interface written in Python and made that the coupling framework. And it's called PyMT, which is short for Python Modeling Tool. And the idea here is it's just a lightweight Python package that allows you to drive models that have been written with a BMI, a basic model interface, directly through a Python script or notebook or shell. So this little code snippet maybe gives you the idea. Here we've created a model as an object, and I initialize it with one function. I change some of its values. Then I have a little loop where I update it sequentially through time. And it's that level of model control. At the moment, the Python modeling tool model collection includes, I guess, 16 or so pre-existing legacy codes that have been wrapped to act as components. They're listed on the left here, and they run the gamut from hydrology, permafrost, landscape evolution, coastal processes, marine and sedimentary processes. In addition to that, components, sort of single process components that have been written with Landlab can also be run through the PyMT. So you have things like a diffusion, a linear diffusion component, or a little kinematic normal fault component. So that's sort of the vision for making coupled model easier. And one of the things that we're hoping will happen over the next couple of years is that this collection of models as components will grow over time, and in particular that it will come to include tectonic components. So where does this leave us now? One of the things that people have made some headway in using these kinds of tools is in what you might think of as kinematic model coupling. So what I mean by this is models where you use a kinematic representation of tectonics. So I'm going to highlight some work of Alison's and Alison's student Sarah in exploring what happens when you have a strike-slip fault appearing in a landscape, offsetting streams and hills and things like that. So this is a simulation that Alison developed. And here's a series of frames from some similar simulations that Sarah Harbert developed and published just a couple years ago. So these are kinematic in the sense that we're not using a 3D deformation model, but there's simply a description of motion imposed in the simulation grid. Well, one of our experiences has been that having Landlab as a flexible toolkit makes these kind of kinematic setup kind of things easier. I'll show just a couple of quick examples of this. So here on the left is an example from Harrison Gray. Harrison was a PhD student, now a USGS employee. And when he was a PhD student, Harrison is interested in luminescence and using luminescence to do all kinds of things. But he was sort of watching as Landlab was being developed, and he got an idea. And he ended up doing a really interesting side project about distributed shear on the San Andreas Fault, which he was able to put together pretty quickly because he could pick up some pre-existing components in Landlab that do landscape evolution and add to that a simple tectonic deformation function, if you like, that looks like this, where it's the hypothesis that tectonics along this stretch of the fault are actually shearing some of the rocks in addition to the motion on the fault itself. And he was able to compare that with field observations. Another example is a paper that Nadine Reitman and Carl Mueller published last fall, where they again used Landlab as the basis for writing a little model, this time for thinking about channels incised into alluvial fans that are being dynamically offset, and using that as a way to think about how far back in time can you see displacement. If I see a particular amount of displacement on a stream on a fan, how does that relate to the actual slip rate? And at what point do the streams start to forget the slip rate because they've been offset and captured multiple times? And then one more example from a paper that Scott McCoy, Dan Hobley, and Will Struble and I just published, exploring the cross-sectional profile of normal fault facets and how they might vary as a function of the erodibility of the rock or the rate of slip and so on. So these are all just examples of how the kinematic erosion tectonic problem becomes easier and more efficient to carry out when you have a toolkit with some standardized parts. What it doesn't really address, though, is the full couple problem that Phaedra talked to you about and that Sam carried out using this coupling between child and flak. And that remains something of a frontier. So I'm gonna, this is my last slide here. I mentioned this workshop that had been held 2 years ago now, exploring some of the issues in the interaction of tectonics and surface processes. And for me, some of the things that had come out of that were, well, one, that we're at the verge of being able to do what you might think of as embarrassingly parallel problems, where you, for example, want to do a sensitivity analysis across a range of different parameter combinations, and you can simply launch one model run per node on a supercomputer. Katie Barnhart just had some papers coming out now that show an example of doing that using 1 million or so CPU hours to do a big uncertainty quantification and parameter optimization. So that's doable. What we're lacking now in the systems modeling framework is we still don't have any 2 or 3D deformation codes that have a basic model interface and that are components in the system. That would be a wonderful step to take. There's still questions about how and whether something like the basic model interface could be adapted for parallel codes. It's, one of the things I learned from that workshop is that when you're doing 3D deformation problems, you really need, for at least a certain class of problems, you really do need parallel computing with domain decomposition. And it's not clear, to me anyway, and people have made some forays into this that I can't really speak to with any great expertise. I'm thinking here of some of Tristan Saul's work, for example. But it's not clear to me whether in coupling a surface process model with a 3D tectonic model, you need to do that at the level of a decomposed domain, or it's feasible to do your domain decomposition for some period of time and then stitch it back together and run your surface process model because it's relatively efficient, or exactly what the best strategy for that is. And so I think part of the technological frontier then lies in sorting out some of these technical issues that would allow us to do model coupling in a faster and more efficient way than has been possible in the past. So that's all I have. I'll stop there and welcome any questions.
Thanks, Greg. That was great. So one question that pertains to some of the stuff that you talked about that came up is, what advice would you give to young scientists, early career, who are interested in getting into modeling, right? It seems like a kind of giant can of worms to jump into. And you know, what, in your experience, where are the best starting points? How do you get going? Is the best thing to go to one of these workshops that CSDMS is going to be running, or are there other ways that you could get in even before that?
Yeah, that's a great question, Mark. You know, one of the challenges here is that numerical modeling it requires several different skill sets at once, I think. One of them is you need to be proficient in computer programming, and to do it in a sustainable way, you need a certain minimum level of proficiency. You need to know something about numerical algorithms. And in addition to that, there is a way of thinking that I have never seen a book or a good resource that teaches this, but it's because numerical modeling is a different kind of intellectual activity from experiments or it requires some familiarity with the do's and don'ts of approaching the problem intellectually. For example, don't make the problem too complicated. Don't try to reproduce the real world. Ask a very clear, well-posed question. And I think the best guide to mastering that is to read the literature and pay attention to those studies that feel like they've really moved the ball forward and done something elegant. But in terms of the nuts and bolts, it's tough. I think that from a simply computing and software skills point of view, at least in the US, we're in a tough position because computer science departments are maxed out. They don't have a lot of extra capacity for people outside that world. And even when they do, they tend to have a focus on more commercial applications, you know, web apps and things like that. So my sense is a little bit that the scientific communities, at least in the geosciences, we're a little bit slow to pick up and try and fill that hole, but there are some resources out there. Fortunately, in this world of online resources, there are some good substitutes. So there's the software carpentry group that has some great scientific software learning resources. There's Data Camp, which is commercial, but you can often get access to it through a university, and they have some good stuff. Students of mine have told me they like it. But I think there's no real substitute for taking a good scientific programming course if you can find one. In terms of books and things like that, one of my favorites is by Rudy Slingerland and Lee Kump. I think it's called something like Mathematical Modeling of Earth's Dynamical Systems. It is probably out of print now, but you can still find it with various booksellers.
I was looking to see if it was on my shelf right here, but it must be on the one back there. So one other thing just on that same topic, or kind of on that same topic, you know, I think it might be useful just to also clear up any misconceptions about whether or not you need to have a giant computer cluster to run some of the models that you've been talking about from CSDMS. I mean, if you're, you know, you want to get into modeling, what do you need? Could you use a laptop, or do you need to have really high-powered computers?
Certainly to get started, you can do it on your laptop. It's always been my experience. It's when you want to scale up that you sometimes run into problems. Not always. I mean, I showed those little animation from the paper we just published. I did that all. I did all that on my laptop. You know, but there's others in the room, quote unquote, here who could speak better than I can to the needs of 3D deformation codes. I think that the FLAC 3D code that Phaedra uses, because of the nature of its solution scheme, this is something you taught me, Mark, because it's a wave propagation code, it is feasible to run on a single processor. Am I getting that right?
Yeah, everything I do is on my workstation. I mean, a lot of SAMs, at Maine, I've got a lab full of pretty powerful workstations, and so, I mean, some of the models end up, you know, if I put high resolution topography on, they can take a day or so, but and yeah, I mean, but it's because it's a commercial code, it's kind of different and not really where we're wanting to go. But yeah, it depends, yeah, the code you're using and what you want to do. But definitely, I think you can, when you're getting started, working on a laptop or a desktop is definitely feasible. I mean, we've got Charles Williams, who's on CIG, and he does some short-term tectonics, and all of his stuff is on Linux cluster at work, you know, so that sort of 3D geodynamic model was quite computationally demanding.
One thing that's maybe worth adding is, well, I'll hold this thought and see if there's any other questions.
Yeah, I don't think we have any others, so if you want to have a final word, both of you, then I think we can wrap it up.
Well, I would say, you know, in terms of numerical modeling, you know, one of the things that, so it's technology and science, and we're used to technology and science, right? We use microscopes to see viruses, and we use telescopes to see quasars and that sort of thing. But what makes computational modeling different is that we're not enhancing our senses, but what we're doing is enhancing our ability to think. Our brains are just not evolved to solve lots and lots of calculations at blinding speed. We're really bad at it as a species. And yet we have these machines, computers, that can do that well. So it's, I think of it as a kind of an attachment to your brain that does the things that my brain isn't very good at.
Going back to that first question about good, you know, advice for modeling, I think, I mean, really, actually, I'm a kind of an exception to what Greg said in that I really can't code. I've learned to do some, to modify the models, but I couldn't sit down and write a model. But I think things that have really helped me is working with the observations and geologists, and all of my best, what I consider my best modeling projects have been very, very collaborative. There's been a lot of back and forth with someone who knows the area or the problem really well, and also having a really clear question. I mean, you do get people coming to say, I want to model this, and it's like, no, but they don't really know what that, they just think that it would be good to have a model. You really want a clear question. You want to know what the process is you're looking at, and so then you can really, because you do have to simplify, and I've been doing this for years and I still make my first model too complicated. So you really have to look at your problem and look at really what you want to get out of it and simplify and really ask questions, and go back and forth with the structural geologist you're working, or the observations that you know. And the other thing is that sometimes you will get unexpected results. Sometimes that'll be because you don't understand your boundary conditions and you've made a mistake, but sometimes it will be because the model is telling you something that is real, and it is actually not the myth that we've believed. So it's kind of a combination of trusting yourself and trusting the model, but also really making sure that you understand those boundary conditions and understand those initial conditions, and so you can have confidence when you do see something unexpected, and really investigating why. But it might be telling you something that, as Greg said, that we haven't thought that way before. I mean, that's really what I see the why we do modeling, is to really interrogate the processes and implications of parameters and why things are happening. So to me, just wanting to build a model to replicate something, I mean, why would you? You want to build a model to answer questions, and often it's the model that doesn't quite work that can really tell you something. Yeah.
Well, I want to thank the speakers here. I think this was a great conversation, and thank our moderators as well. And of course, everyone, thank you for joining us. We'll see you again next season. Thank you so much.
Thank you.